Okay, here we are. This is activity 2, chapter 5. We're going to do experiments 1, 2, and 4. Experiment 1 is a simple, demonstration to find out is there evidence of particle motion in liquids. Okay, remember this chapter is about the small particle theory of liquids and solids. So we're going to use a liquid, and we're just going to use regular water. And actually, you can do this one at home. It's very simple. I'm sure you've all seen this done before. We're just going to use some water and food coloring. And a lot of teachers use liquid watercolors instead of food coloring. If you're going to use a lot of watercolor or food color in your classroom, this little bottle of food coloring is about $5. And you can get a huge, like a pop bottle full of liquid watercolor for $2 or $3 at discount school supplies. So make sure if you're going to do a lot with food coloring that you actually buy the liquid watercolors. This stains a lot and the liquid watercolors doesn't. Now at home you can do this and you can try different temperatures of water. The water I'm using is room temperature water. Okay, just plain old tap water that's at room temperature. I'm going to pick the blue food coloring first, and all I'm going to do is put a drop into the beaker. Alright, so we're going to that down, and let's see what happens here. Okay, so we're going to watch that for a second, and it looks like blue might not have been the best choice of color. So let's try another one. Oops. Looks like blue might not have been the best choice of color. So let's try another one because the background is blue. Okay. Alrighty, so I'm going to use, let's try red. And you know what? This might actually work better if our cameraman Steve kind of zooms in on this beaker down here. And let's see if we can see what happens a little better here than on the document camera. So, okay, so here's a drop of food color. And yeah, I think that's better. So we're going to observe that just for a little bit. Remember, the question is there evidence of particle motion in liquids? So if you look at, we put a white background behind this. Is there evidence of particle motion in liquids? You might be able to see that the red dye I put in one drop is kind of spreading seemingly on its own. You can try this at home. Just get some food coloring or some liquid watercolor and try that at home. So now you have several questions to answer, and you need to answer those. The next question that we're going to try and answer in experiment 2 is there space between particles of solids? So I think, again, we might be better off just zooming in on this section here. And students, I tried this morning in the lab, and it was very interesting, the results I got. Very, very interesting. So what I did is kind of expanded the experiment. So in the textbook it says, or in your workbook it says, use marbles and sand. And what I've done is I've used the white, larger marbles, and then I have some clear, these are like little tiny marbles. Okay. And then I have some kind of flat glass beads like, and then I've got some sand. Okay. So, Dr. Moyer and Dr. Otto and a bunch of us were talking this morning, and I was describing what happened with this experiment, and Dr. Moyer came up with a really good idea that our question we're trying to answer is there space between particles of solids? And it depends on the shape of the solid. So instead of comparing round white beads to sand, as the book says, instead we will be comparing large round and small round, and then we'll be comparing sand and the more flat glass. So let's see what happens. Okay. We're going to start, as it says in your book, we're going to fill the beaker and the other things, we fill them all to 100 mils. And now we're going to pour 50 mils of water into each of 4 graduated cylinders. Each of the cylinders is going to be associated with one of the beakers. So we're just pouring in, again, room temperature tap water. Pouring that into each beaker. So I've got. Now remember, in your book, there's just 2, but we all were discussing this morning, and we thought it would be much better if we compared round to round and flat to flat. So, okay, so I'm going to step around to the front of the table, and what I'm going to do now is I'm going to add to each of these containers, I'm going to add water to fill the space between the sand particles, the marbles, the flat glass beads, and the little marbles. So I'm going to add water until I see the water reach the 100 milliliter part. Let's go ahead and try that. I'm trying to get to the level of 100 milliliters. We're going to let the sand kind of soak that up for a little bit. And the water's not quite at 100. Whoops! Okay, now I'm over 100. So let's go back here. Okay, I'm at 100. Lost one of the beakers in the meantime. Which in science is messy, right? That's what we all know. Okay, now I'm going to take the flat marbles, okay, and I'm going to pour until I hit 100 milliliters here. Okay, you're going to have to trust me that I'm going up to 100 milliliters on each one. Okay. Now I'm going to use the small round glass beads. Okay. And let's go to 100 here. Pour it a little bit closer. Okay. And now I need to pour a fresh one. Okay, let's see. This is the one that I spilled. Okay, so I've got the 50 mils of water again, and now I'm going to do the large marbles. Okay, let me just make sure that the sand. So, students, remember the question that we're asking is there space between particles of solids? Okay. These are all solids. They're different size particles, and they're also different shape particles. So, your book says that we're to observe the water level in the graduated cylinder in the space below and record the final volume of water in the graduated cylinder. Okay, so the large white marbles, the final volume is 7 milliliters. Okay. We started, let's see if this will help you see it better. Not really. You're going to have to trust me that it's 7 milliliters. We started with 50. So the volume of water we needed to fill in the area between the large white marbles was 50 minus 7. Okay, so when it says what volume of water was added to the beaker of sand, we're doing the white marbles first, so put white marbles, 50 minus 7, which is, you all know, 43, right? 43 milliliters. Now we're going to do the small marbles. We're going to look at the volume of water left. In this case, the volume of water left is 8 milliliters. So that means we started with 50, we have 8 left, so that means there's 42 milliliters in the small round spheres. So what volume of water was added to the beaker of small marbles? We added 42 milliliters. Now we're looking at the flat glass beads. So what volume of water was added to the beaker of the flat glass beads? We have 11 milliliters left. So 50 minus 11, we used 39 milliliters for the flat beads. And for the sand, we have 15 milliliters left. And remember, when you're reading a graduated cylinder, you should look at eye level where it's at. Okay, so you read at the top, and we've got 15 milliliters left, so we use 35. Okay, so now you need to answer the question. If the total volume occupied by sand and water is 100, what is the percent in the beaker that was water? Okay. So we've got 100 milliliters, and so you're simply going to take the number that we had, 43 milliliters, 42, 35, that is the percent water. Those numbers are the percent water. So what I want you to compare is the similarly shaped particles. So I want you to compare, when you answer the question, how does the volume of water to the marbles compare to the volume of water between the large marbles and the smaller marbles? How do those two numbers compare? Because we discovered this morning that shape does matter. Okay? And how do these two numbers compare? So in that question, and now it says, in both systems, what does the volume of water added represent with respect to the small particle theory? So the water is representing what? The actual particles or the space between particles? You need to answer that question. Okay, and then you have to answer the questions, the next two questions. All right, experiment number 3 involves a simulator, which you will do on your computer. Okay, so we're going to skip through the book now, and now we're going to go to experiment number 4, where we need to answer the question, is there evidence of forces between particles? Okay, so remember in experiment 1, our question, is there evidence of particle motion in liquids? And I'm picking this up now to show you that the red is completely evenly distributed throughout this whole beaker. So that was the first question. The second question, is there space between particles of solids? And then you followed that with your simulator, which you've now completed. And now we're on experiment 4. Is there evidence of forces between particles? So what we're going to do here is, as it says in your book, we need wax paper, water, ethanol, hexane, and we're going to need some droppers. Okay? So we've got all those materials. I'm hoping that the dock camera will be able to pick up what we're about to do. Okay? Now, if you ever use hexane or ethanol in a classroom, number 1, you have to use goggles. Okay? especially hexane or ethanol. What you can use, which is a little safer, is you can just use rubbing alcohol in your classroom. You may not be able to get ethanol and hexane. Okay, you definitely will be able to get water though. All right, so here we go. We need a piece of wax paper. Okay, and again, in your own classroom, you might be able to. You might be able to use just regular rubbing alcohol that you can get at the drugstore. Okay, I am going to take a drop of water and I'm going to put it onto the wax paper. I hope you can see that drop of water on the wax paper. Now I'm going to take a drop of ethanol and put that on the wax paper. The ethanol. Okay, it's kind of hard to see. I can barely see it. Let's see if I can get a better background here. Maybe if white would be better. Okay. Minor difficulty here. Let me get a white background and see how we do that. A little bit better. Okay. All right. And that was the ethanol. So I'll just write ETH for ethanol. Maybe you saw that drop moving when I wrote. Okay. And then the third one is hexane. Hexane is kind of a dangerous substance, so you will not find it probably in your school. It smells too. Okay. The hexane is basically flat. Okay. It's evaporated completely. It's completely flat. The ethanol is a little bit of a bump right here. You can notice that. And the water, let's have some fun with the water. Okay? So the water, I can take and I can move around on the wax paper. You can do this at home. In fact, I will give you some of these droppers. You can see I've kind of made the water into several different pieces. I'm going to, no, that's not going to work. You can kind of see that they have a shape, and you can do this at home even with a drop of water that you put on your finger. Just put a drop of water on your finger and you can do the same thing with it. But the water, I can actually take the pipette, I can break it up into smaller drops, I can make it into larger drops, which is basically what rain is. It's just a bunch of small little pieces of water that have come together. So in your book, it says, observe the water droplet from all angles and describe or draw what you see. Okay, so with the water droplet, you can, like I say, use the dropper I've given you, or you can just put some water on your finger and drop it onto the wax paper and record what you see. And then drag the pipette through the water and record that. And then the question is, what evidence do you have that forces other than forces due to colliding and bouncing exist between particles of water? So when you play with the water droplet and you move it around, you can move it with your finger and you break it into pieces and you bring them back together and you make them dance. Okay? When you're doing all that, the water, remember what we're looking for is there evidence of forces between particles? So answer that question. Now we're to put single droplets of ethanol and hexane on dry parts of the wax paper. Okay? The ethanol, we can still see right here, is circular. Okay, we can still see that. Now, can we take and make it into bigger and smaller drops? Not really. It just kind of flattens out. Okay. You can try this with rubbing alcohol if you have some at home. You can try this out. It won't be quite as dramatic. Now, the hexane, on the other hand, the hexane is completely gone. Okay. The hexane, as soon as I dropped it on the wax paper, flattened right out and evaporated. Okay, so step 4 says to put the ethanol and the hexane and describe and or draw the appearance of each droplet when applied to the wax paper. And now you have some questions about the appearance of the droplets. What does the appearance of the droplets and their behavior say about the strength of the forces between the particles? In other words, which liquid has the strongest forces and which has the weakest forces? Then your book says that I'm going to show you a video clip of an experiment performed on a stream of water. That is on C-Tools. You'll find that on C-Tools. It might be called Water Drop or something, but that is on C-Tools, so you can find that on there. And that ends our Chapter 5, Activity 2, Experiments. Thank you.